So, haloalkanes are just any alkane, so any compound that's made up of single bonded sp3 carbons and hydrogens. So a haloalkane is just any alkane that contains any number of halogens at any place, substituting for a hydrogen. So let's recall the halogens are fluorine, chlorine, bromine, and iodine, from smallest size to largest size. So these are small, large, and these have the highest electronegativity So fluorine is both the smallest and the most electronegative halogen. And as to why exactly that's important, we'll get to that in a little bit. So, like I said, this is a haloalkane. So is this, and there are literally infinite examples of haloalkanes. But let's start off with how haloalkanes are made. So, a haloalkane is generally made in one of four ways. First, it can be made from alcohol. So from alcohols. Second way that you can make a haloalkane is from alkanes themselves. The third way is from substitution of the halogen that's attached to the alkane. Substitution. And finally, and this is the easiest one, is you can make them from alkenes. So, let's just go down this list and I'll show you the electron pushing mechanisms for how each of these are made. So supposing you wanted to make, what I'm going to do is I'm going to use this haloalkane as my example for what I'm trying to synthesize as the target of each of these four. So, to start off, from an alcohol, what the compound you would start off with is this. And essentially all you're doing is you're substituting the alcohol group for a halogen group. Because remember that all of these have a minus charge, and so does an OH group. So the way you do this is you introduce a halogen acid into the system. So keep in mind that HCl, HBr, and HI are all strong acids. And strong acids tend to deprotonate very easily and tend to ionize very easily. So what happens is within solution you have H plus ions, and you also have, I'm going to use bromine in this example, but you also have Br minus. So these are just the 8 valence electrons that are around bromine in its outermost shell. And whenever I do electron pushing mechanisms, I like to highlight the valence electrons of non-organic atoms within the system, just so I can see where electrons are going. So generally what you have happening is if you introduce hydrobromic acid to this compound, what will happen is these electrons on the oxygen have the ability to come around and grab this proton, because this proton is basically the definition of a nucleophile. the definition of an electrophile. So once that happens, the next step is you have this oxygen, which has one lone pair instead of two and three bonds. So now this oxygen has a plus charge, and your bromine, it still has a minus charge and is still in its ionized form. So what happens is this bond between this carbon, which is known as the, let me draw that a little bit bigger. This is known as the alpha carbon. The alpha carbon to oxygen bond is always going to be electronegative towards this group. And that's because oxygen and really any halogen that you put on this is going to be more electronegative than the carbon. So what you're going to have is you're going to have a slightly negative charge here on this end of the bond, and on this end of the bond you're going to have a slightly positive charge. So this opens up the alpha carbon for attack by a strong nucleophile, which any halogen is a strong nucleophile. So what's going to happen is the bromine is going to come in and is going to attack here and form a bond. These electrons are going to come back and resolve the positive charge on the oxygen, because oxygen itself really does not like to be positively charged. So what you end up with is you end up with this. And as you can see, that's our target molecule. So one thing to note with this system is I've not drawn the OH in either dash or wedge, and that's because it can be both dash or wedge. And what's important to note is that in this reaction, the stereochemistry is going to reverse. Why? Because let's assume for simplicity's sake that the OH is a dash. So now if we look at this molecule lengthwise this way, we're going to see we have the methyl group sticking here. We have a hydrogen, we have a hydrogen here. And then going backwards into the board is this carbon. And then coming out this way we have the oxygen. So when this gets protonated, this OH group is bigger than obviously this hydrogen. So bromine itself is a very, very large atom. And so bromine coming and attacking from this side, which is this space, which is already occupied by the OH, is unlikely. So what's going to happen is bromine is going to come in from this side, and it's going to push this hydrogen across to this side of the molecule. So what you start out with is this, what you're going to end up with is something that looks like this. And now, because this carbon is an achiral carbon, what you've done is you have now, because this carbon has unique stereochemistry, what you end up with is you end up reversing the stereochemistry of the carbon. In this case, the stereochemistry is S. So this is an S carbon going to an R carbon, if that's important to you. So that's how you get to make haloalkanes from alcohols. So now let's go over the next mechanism, is how do you make a haloalkane from a bromine? How do you make a haloalkane from an alkane itself? So now that we've gone over making a haloalkane from an alcohol, let's start off with making a haloalkane just from a simple alkane. So one of the challenges with making a haloalkane from an alkane itself is that haloalkanes are, alkanes themselves are very, very stable. Carbon-hydrogen bonds do not like to be broken. And so you need exactly the right conditions for this carbon-hydrogen bond to break. So I'm just going to illustrate this hydrogen, which is this hydrogen is the one that will be eliminated from the system when it is attacked by a halogen. So keep in mind that all halogens in their natural form in the environment are diatomic, right? So what is that? So just as a review, a diatomic atom is simply the smallest possible unit of pure fluorine. So a diatomic atom is the smallest possible pure form of an atom. So diatoms are hydrogen, nitrogen, oxygen, fluorine, and all the halogens. So for example, this is how fluorine is formed or found in the environment. So what I'm going to do is, because I'm going to try to make a bromoalkane, I'm going to show you Br2 and how this mechanism works. So what happens is Br2 is introduced into the system, usually as a gas, but that's dependent on what temperature you're at. What happens is, if we introduce now light into the system, what light is going to do is light has the ability to break apart this bond, to break apart this bond. However, bromine can't be Br+. If it were to fully break apart this bond in an ionic sense, you'd end up with Br- and Br+. However, bromine really does not like to be plus. It barely likes being neutral charge. So what happens is, and these arrows are called fishhook arrows if you're not familiar, but what happens is you end up breaking the bond this way. So one electron goes to each atom within the diatomic system. So now, essentially what you have is you have radical Br. So this is very unstable, and it really doesn't like having 7 atoms around it. And since it's not diatomic anymore, it really wants that either another electron or it wants a bond that can stabilize this free radical. So what ends up happening is this ends up coming down and fishhooking with this hydrogen. And one electron from this bond merges with this one electron to make the carbon-bromine bond once again here at the alpha carbon. Then you end up with, in the next step, what you're going to end up with is you're going to end up with bromine. So now bromine has its bond and bromine is happy. You're going to end up with a hydrogen radical and a Br radical. Obviously this is happening at the scale of millions and even billions of molecules at a time within a reaction flask, but this is just showing on the single molecular level what's going to happen is this bromine can either go one of two ways. First, it can go and disrupt another Br2 within the system, thus making another bromine radical, or it can go and once again disrupt an alkane and make this bromoalkane, or this can fishhook, draw that a little bit better. This can fishhook there, and you can form HBr, but most importantly, you form your target bromoalkane. Alright, so next I'm going to show you how you can make a haloalkane from substitution. So, making a haloalkane from substitution. So this reaction is essentially the same as making a haloalkane from an alcohol, because all you're doing is you're substituting one halogen atom for another. So, this reaction is going to come with its own special set of rules, which I'll go over in a little bit. So, okay. So the important thing to note with this system is that smaller halogen atoms can only be halogen atoms that are already part of a haloalkane can only be substituted with halogen atoms that are larger than itself. So fluorine, for example, can be substituted for a chlorine, a bromine, or an iodine. But if you had a bromine, which is our target molecule, that bromine can only be substituted for an iodine. It cannot go backwards down the size order. So starting now with this fluoroalkane, essentially all we have to do is switch this fluorine for a bromine. And what you do is within the reaction, you introduce hydrobromic acid. So what happens is, remembering that this is a strong acid, this is going to deprotonate easily. So we can write this as H plus and then Br with all of its electrons around it minus. So essentially what happens is this is a quick one-step substitution mechanism wherein you have your leaving group and you have this bromine coming and attacking. This fluorine, once again, has 6 valence electrons around it. This bromine comes in and attacks, and what happens is you form this 5-bonded transition state. So, you already have a hydrogen bound to this carbon. You have the fluorine, but now you have this partial bromine bond here. So it progresses through this transition state. Now, transition states are very unstable. And usually you would have, I'm assuming that in this case you have the right reaction conditions to drive the reaction entirely in this direction, so as not to reverse it back to its original product, which it is likely to do. So what happens from this transition state is, you remember you have that free-floating hydrogen. So that can be attracted by the fluorine. That comes and fluorine leaves, and this bromine bond just solidifies. So what we have then here is we have our target haloalkane. So what's important to remember again with this system is that much like the OH substitution, it's essentially the same reaction, it just happens in a much faster single step, is that you will end up with a reversed stereochemistry because the bromine, being much larger than the fluorine, has to attack from the other side. You can even make this by going fluorine to chlorine to bromine, but I did it in one step just to get to our target molecule as quickly as I could. So in the next step, we'll be learning about how to make haloalkanes from alkenes, which personally I think is probably the easiest mechanism. Okay, so I'm going to be showing you now how to make a bromoalkane from an alkene. So I'm going to assume that we're, draw that a little bit better. I'm going to assume that we're starting with this alkene. And what we need to add, so keep in mind that there's one hydrogen atom here and one hydrogen atom here. So all we need to add to the system to make that is we need to add one hydrogen atom here, and we need to add one bromine atom here. So in order to do that, what we're going to do is we're going to introduce, once again, our old friend HBr into the system. And once again, I'm just going to write it as H plus, Br minus. So this Br minus, keep in mind that what happens with this is these electrons within the bond here are going to go and attract this hydrogen atom. And what that does is that leaves what is known as a carbocation, which is just a positively charged carbon. So now you have two hydrogens around here, so I don't need to draw them out. And you have only one hydrogen here, so you have this carbocation. Then what happens is bromine is going to come in, see the carbocation is going to attack it. And keep in mind, because it's a carbocation, it has a trigonal planar geometry. It has a trigonal planar geometry. So this bromine can attack from any side. So once again, we're not going to be concerned with stereochemistry. We're just going to draw this as if it can occur in both scenarios, as if it can result in both stereochemical outcomes, which is equally possible. So what happens is we have this bromine attacks this carbocation, and once again, we end up with our target haloalkane. Now, when we're making these haloalkanes via this mechanism proceeds via a carbocation. And carbocations in general like to be bonded to other carbon atoms because that helps stabilize the positive charge. As carbon really likes to be neutral, it doesn't like either a positive or negative charge. So, for example, you have primary carbocations, which are essentially just a CH2 and a plus instead of a CH3. Then there are secondary draw that a little bit bigger. There are secondary carbocations, which this is an example of a secondary carbocation. And then finally, the most stable of all carbocations is this. That's the tertiary carbocation. So whenever you're creating any compound that whose mechanism proceeds via a carbocation, you need to think about which carbon is going to end up with, in this case, the bromine, and which carbon is going to end up with the hydrogen. With our starting molecule, because the starting molecule is symmetrical across this dotted line plane, this and this, so the two carbons within the bond, are the only possible carbons that anything can be added to. However, in this case, both of these carbons are exactly identical to each other. Both of them are secondary carbocations. And so what that means is that even if you add it to here or to here, you're still going to end up with this compound. And most importantly for this context, both carbocations are equally stable. However, if I gave you this molecule here, for example, where now the double bond is here, between a secondary and a primary carbocation, or secondary carbon and a primary carbon, which would be the most likely product? Would the most likely product be 1, 2, 3, 4, 1, 2, 3, 4? Would that be the most likely product? Or that be the most likely product? Well, let's think about it in terms of a mechanism. If you want the bromine is always going to attach to the carbocation. So, if you want the bromine to attach here, what you would need for this system is you would need a carbocation to be here. What you need for this, conversely, is you would need your carbocation to be here. And remember that a secondary carbocation is more stable than a primary carbocation. So this is the product that's going to be made, even though there's the potential for you to make this product. This is going to be the primary product if you introduce hydrogen bromide or bromic acid to this compound. This principle that deals with the stability of carbocations in substitution reactions is known as the Markovnikov rule. And all the Markovnikov rule states is that in terms of stability, a tertiary carbocation is more stable than a secondary carbocation, which is much more stable than a primary carbocation. And that's all you need to know about formation of carbocations and the Markovnikov rule in the context of forming haloalkanes. So now I've gone through the formation of haloalkanes. So now that we've gone over these 4 ways to make haloalkanes, let's talk about another special kind of compound called haloarenes. So haloarenes are difficult because haloarenes are essentially halogen atoms that are attached to a benzene ring. So aromatic compounds are compounds that contain 1 or more benzene rings. Now, what's unique about a benzene ring is that this is an entirely pi conjugated system, so it's very, very, very stable. Addition of anything to a benzene ring, if you want to maintain what is known as the aromaticity, or the this perfect pi conjugated system, what you're going to need to do is you're going to need to substitute. There's no way you can add, because every single carbon here is sp2 hybridized. So if I were to add, for example, a chlorine atom here, then that would mean that now this would be negatively charged. This would be an sp3 carbon, and so you could not complete this nice round pi conjugated system. So what has to happen is a chlorine or a bromine or any halogen has to take the place of this hydrogen. And that reaction itself requires a lot of energy input, because you're moving from you're trying to disrupt a very stable compound, which is not going to happen unless obviously you have a lot of energy. But what I'm going to do is I'm just going to talk you through this system very quickly. And all it really involves is the breaking of aromaticity and the reformation of aromaticity. Excuse me. So let's say we start off with this hydrogen. We're trying to substitute it for chlorine. What you need in this reaction is, first of all, you need a lot of hydrochloric acid. So what happens is you end up with chlorine coming and attacking here. These electrons then kick to this carbon and make it negative. So now you have a carbanion. So now what you have here is you have a hydrogen and a chlorine. Here, whoops. So what you have is I'm just going to redraw that a little bit bigger. Okay, so now you have this ring. Now notice that this ring is not aromatic because every single carbon in here is not part of the pi-conjugated system. This is now sp3 hybridized, while everything else is still sp2. So this is the first step, which is the breaking of aromaticity. Now what you need to do is you need to reform aromaticity. So to reform the aromaticity, what happens is these electrons are going to kick back and they're going to kick off. They can either kick off the chlorine, which makes this reaction reversible, or they can kick off this hydrogen atom, which since the electrons are kicked off with it, this can go and actually link up. This is a hydride because it's a hydrogen plus 2 electrons. So this can actually go and link up with the H plus from the previous step. And what you'd end up with is you would end up with this as your product. And you'd end up with, H2 gas. So the important thing to remember when you're looking at haloarenes is the mechanism consists of 2 things: breaking of aromaticity, which is here, and the reformation of aromaticity, which is here. Because benzene is very unstable and really doesn't like things added to it, this portion, the reversal of aromaticity, can be thought of as a reversible step, because this can either revert back to the pure benzene it was, or it can move forward to become a chlorinated benzene at one position. So we'll get to more benzene type reactions later on, but for now all you really need to know is that this mechanism is fairly standard for most or all nucleophiles that you'd like to attach directly to the ring. You need to break aromaticity and reform aromaticity, even though this step is reversible and highly volatile. So with that, I'm going to leave you until the next lesson.